Here we go. Today we're going to talk about the isosceles triangle theorem and converse of the isosceles triangle theorem. Okay, so we'll get to that. But before we do, I want to give you some vocabularies that you should know. I think a lot of you already know this. So if you have an isosceles triangle like this, the angle, okay, first of all, you have a base, right? And you have the two legs. Two legs are the congruent legs, right? You understand? And guess what these angles are called? Where the base is. Okay? And then guess what this angle on top is called? Okay, of course, it could be rotated, but many times when you have an isosceles triangle, especially if only two sides are congruent, right? Then you have this picture. Could you have three angles to be congruent?
Yes.
It's still an isosceles triangle, isn't it? Because what do we say? Definition of isosceles triangle says, yes, sir. At least two sides. But if you do have two sides, then this is what you get, right? And you could have three sides too, but it just happens that all three then sides will be congruent. Okay, so then any sides could be base if all three sides are congruent. Does that make sense? But normally you would only have two sides, right? So the size that's different will be the base, and then here's your vertex angle, right? Opposite of that base, and then two legs and base angles. Is that okay? So we need to know that first before we talk about the isosceles triangle theorem, because it's going to use these words, okay? Or use these terms. Okay, anybody need more time to write this? Yeah? Okay. Yeah. You got the base. Yeah, go ahead and draw this. You don't have to write this. Just draw the picture. And so this is a vertex angle, base angles, and legs. Okay? Go ahead. I'll wait. So looking at this picture, can somebody tell me something about the base angles of this isosceles triangle? One person see it? 2, 3, 4. Grace, what do you think? They're congruent. How many people agree with Grace? You are correct. If you have an isosceles triangle, right, the base angles are going to be congruent. Guess what the isosceles triangle theorem says? Yeah, that's what it says. Okay, so write this down. That's exactly what it is. Okay, so oops. Here, isosceles triangle theorem. If two sides of a triangle are congruent, then guess what? The angles opposite of those sides, which are called what? Base angles, all right? Okay, then the angles opposite of those sides are
Is that the name?
congruent. Yeah, it's got a name.
Okay.
So isn't that nice? Yeah, so you could use the name, but at least write it once. And here's a picture. Move it up. So exactly what you thought of this. Okay, exactly what you said. So if you have an isosceles triangle, they don't really say isosceles triangle, do they? They just say if two sides of a triangle are congruent, right? Then the angle opposite of those sides, we know them as the base angles, right? The angles opposite of those sides are congruent. So that's the theorem. Very simple. So if AB is congruent to AC, guess what? B and C are congruent. Angle B and C are congruent. Let's look at how we could go about proving this thing. Okay? So look at the triangle that they gave you. In this triangle, what's given to us, guys? Kevin?
Segment AB and segment AC.
Yeah, segment AB and segment AC are congruent, right? That's all that's given. What do they get this dotted line and these marking over here for? What do you think that's for? Anybody? Yes, sir. Yeah, that's going to be something that's going to be helpful for our proofs. If you want to prove this, you need to draw this AD. Guess how we're going to do that? Anybody remember? That's called what kind of line is this called? Yes. An auxiliary line. Okay, so we're going to have to draw an auxiliary line this way. How? What kind of auxiliary lines are we going to draw? Yes. Hint, hint. Look at the red marking over here. Right. So the auxiliary lines are dotted. But how are we going to? What kind of lines do we want, Tony?
We draw the auxiliary lines so the AD bisects angle BAC.
Exactly right. So we want to draw an AD so that it bisects the angle BAC. That's the idea. Okay? So whenever they put these things in the proof, like a picture, that's sort of a hint that that's what they're going to be doing, and that's going to be helpful for us. Okay? So then how is that going to be helpful for us? To show that if AB is congruent to AC, that angle B is congruent to C. Josh? Exactly. Basically, all you have to do is prove that triangle ABD is congruent to triangle. No, if I said ABD, you should say ACD. ABD will be congruent to ACD, right? Yes, question.
So is that
that given that angle BAD is congruent to CAD?
Well, because we drew this auxiliary line in a way, such a way that it's a bisector of BAC, by definition, angle bisector, yes, you could say ABD is congruent to ACD.
So how are you going to write that?
Okay, we'll actually talk about that later. Yes, good question.
Can't you just say AB equal to AC, and then do angle B equals angle C?
Okay, why, Jason?
That's not really
Okay, who could tell me why we can't use isosceles triangle theorem to prove isosceles triangle theorem? Okay, yeah. So you can't use that, because if you could do that, then you're done with, right? All the proofs are easy. Okay, so just remember, I know it happens sometimes, right? But yeah, you're right. It's saying exactly that, but we can't use that. So the way we're going to prove is, we're going to show that triangle ABD is congruent to triangle ACD. And Austin asked a good question. How are you going to say that? Well, don't worry about that for now. So but is there an auxiliary line? Is there a line that bisects the angle BAC? Yeah, there's an angle. I mean, there's a bisector that will bisect angle BAC, right? That's what we're drawing now, right? And if it does, then we know that this angle is congruent to this angle right here.
But don't you have to write first that AD bisects BAC?
Yeah, so we'll show you if you wanted to know how to do that in a minute. But we're going to draw an auxiliary line such a way that AD bisects angle BAC, and the bisector, right, hits the segment BC at D. Is that okay? Now, then how are we going to show that angle B is congruent to angle C? Anybody? Right, a lot of people see it now. Okay, Jason, why don't you try it again? Not yet, because you have to show that the...
like angle, no, side angle side.
Yeah, you have to use side angle side. And if this is sort of obvious, right? Look, AB is congruent to AC, and the... Yeah. The AB is congruent to AC, right, the size, and then the included angle right here, right? This angle is congruent because that's how we drew this auxiliary line, right? And of course, AD is congruent to AD. Therefore, the two triangles are congruent by side angle side. And so, what about B and C? They're congruent because corresponding parts of congruent triangles are congruent. Does that make sense? So that's how you go about proving it. Are we okay with that? Okay. So from this theorem, though, we get some corollaries. Okay, so take a look at the first one. It says an equilateral triangle. What kind of triangle is equilateral triangle?
All congruent.
All congruent sides, right? Very good. An equilateral triangle is also an equiangular. Why is that true? And again, this comes from the theorem above. A lot of people see it. Okay, people still writing. Let me wait. Okay, go ahead and write it down. And as you write it down, think about how you would actually use that theorem to prove this. Okay, think about it. So who thinks they know how to go about proving this corollary using the theorem above? How about, you know, using the isosceles triangle theorem? How? Yeah, all the sides are the same, so. Right? Right. So basically, how many times do you use this isosceles triangle on? Just you do it. You use it twice. Look, like imagine that you have, right, an isosceles triangle. I mean, imagine that you have an equilateral triangle, right? So let's say that this ABC is an equilateral triangle. Okay. Then you could say, well, using the isosceles triangle theorem, that B and C are congruent, right? And just rotate that triangle, and then use the same theorem for angle A and C. Guess what? Then all three angles are congruent, right? By transitive, you could say that. Right? You see how that works? Okay. Any question? So you basically use this twice and use transitive, right? So forth.
Wait, but that's not an equilateral triangle.
I know, but if you have an equilateral triangle, that's what corollary is saying, right? It says an equilateral triangle is also equiangular. So you basically use this isosceles triangle theorem twice, right? And say all three angles. Yeah. Yes.
It's not a mention of the corollary, but if you notice, it says it's often stated as follows.
Mm-hmm.
Do we have to write the follows in proofs, or can we write
No.
the isosceles triangle?
Yeah, just isosceles triangles. Yeah, just use isosceles triangles. Fine. Okay. All right. So let's look at. That's a good point. Base angles of an isosceles triangle are congruent. Sometimes they use that. Okay, that's a good point. So you could either use isosceles triangle theorem, or if you want to use base angles of an isosceles triangle are congruent, that's fine too. Good question.
Definition.
No, it's not definition. Okay, is this a definition? Base angles of an isosceles triangle are congruent? No, it's not definition of an isosceles triangle, is it? Definition of an isosceles triangle only states that
Isn't that like the definition of base angle?
no. It's not. Definition of base angle is not. They just tell you what base angles are. They don't tell you that they're congruent. The theorem is the one that tells you that they're congruent. You see the difference? All right, let's look at the second corollary then. An equilateral triangle has what?
60 degrees.
60 degrees. That's easy. And do you see how this is sort of combination of the previous theorem, the isosceles triangle theorem, and the corollary, and also the fact that sum of the angle of a triangle is
180.
180, right? And of course, all three of them are same. You divide it by 3, you get 60. So who wants to read then the last one for this theorem? How about, okay, Kevin, go ahead.
The bisector of the vertex angle of an isosceles triangle is perpendicular to the base of its midpoint.
Yeah, okay, so what does that mean? It's sort of long, but let's look at the picture again. So it says the bisector of the vertex angle of an isosceles triangle is perpendicular to the base at its midpoint. I'll wait, go ahead and write it down. And let's talk about what this means, okay? How many people think they know what this is saying here? Okay, 1, 2, 3, 4, that's it? Anybody on this side? Oh, okay. Go ahead. Brianna, what do you think? What does it mean?
When it like bisects the vertex,
Right?
the base is perpendicular because the base is like straight too.
Okay.
Bisector it goes in the middle.
Okay, so first of all, you're right. When it says the bisector of the vertex angle of an isosceles triangle, which one are they talking about in this picture? Yeah, which one? Raise your hand, raise your hand. Okay, how about who haven't I called today? How about Esther? What do you think? In this picture on top, which one are they talking about? The bisector of the vertex angle of an isosceles triangle.
Bisector and the top angle is like it meets in the middle of the base.
Yeah, look at the picture up here. In this triangle ABC, which one is the bisector of the vertex angle of an isosceles triangle? AD. How many people agree with her? Anybody have a different answer? How many people are not so sure? She is correct. It is AD. You see, this is the bisector. Isn't this how we drew this bisector, AD? You have the vertex angle at A, right? Isn't AD the bisector of the vertex angle of this isosceles triangle? Right? Okay. And what are they saying? That angle is what? Perpendicular to what? To the base. Not only that, it's not only is it perpendicular to the base. Which one is the base in this triangle? Everybody, what is it? BC. Not only is it perpendicular, it meets at the midpoint, right? Why? How would you go about proving this? Using the theorem we just talked about? Okay. How would you know that the bisector of the vertex is AD is going to be perpendicular to BC and also it meets at the midpoint? One person knows? 2. 3. Okay, go ahead. Talk to your group. Remember, go ahead, discuss. So, how about who? I haven't called.
You have
All right, go ahead. Thank you.
okay.
Right.
So since 80
Yes.
bisects BAC.
Yes.
Then
Sorry, let me show you the whole thing. Here, go ahead.
Then
Oh, I'm sorry. Here.
the two angles are congruent.
Which two angles?
BAD and CAD.
Right.
And then so AB and AC would be congruent because it's isosceles triangles.
Yeah.
And then the auxiliary line
Right.
is congruent to itself.
Yes.
So you get side angle sides, and then you get CPC, TC, and then you can see that those two.
Oh yeah. Yeah.
But that's a long
So that's how you prove that theorem, isosceles triangle theorem. But what this corollary is saying is saying a little bit more than what this theorem is saying. It's saying that AD is going to be perpendicular to BC, and also that D is the midpoint of BC.
Then ABC would be.
Why is then AD perpendicular to BC? Who remembers? Okay, how about Samantha?
So when we were proving
Right.
the theorem,
Right.
we said that triangle VAD, or the triangle VAD is congruent to triangle CAD.
That's right.
So which means that BD has to be congruent to CD.
That's correct. Do you guys agree? Class, we showed, as we were proving this, we know that the two triangles ABD and ACD were congruent, correct? So therefore ADB, it has to be congruent to ADC, right? Now coming back to Andrew now. That's what you said. So knowing this, does it say they're perpendicular? No, but how do we know that they're perpendicular? What tells us that then they're perpendicular? You see what I'm talking about? Because this corollary says that they're perpendicular. We haven't said they're perpendicular. We know they're congruent because those are the corresponding parts of the congruent triangle. How do we know that they're perpendicular? Okay, 1, 2, 3, 4 people. Let me give you a hint. Samantha, give us a hint. How would you say? What would you say?
It's one of the theorems from like one of the past chapters.
Right. If two lines
Oh!
form.
Oh, never mind.
No. Okay. If two lines. Okay, go ahead, Esther. If two lines form congruent adjacent angles, what do you know? Then the lines are perpendicular.
Oh my.
Do you guys remember that one?
Wait, if two lines form congruent.
Yeah, if two lines form congruent adjacent angles, then what? The lines are perpendicular. That's therefore, don't we have two lines forming congruent adjacent angles?
Oh my. I hate
Yes?
myself.
Now,
So hard.
okay, then how do I know that D is the midpoint? That one's easier.
I know.
Yes,
Because you can prove that the two triangles are congruent.
right?
And you can use the CP, CTC,
You can't say that. What does that mean?
the corresponding parts of the congruent triangles are
Exactly. Because the corresponding parts of congruent triangles are congruent, we know that BD is congruent to
these
CD. Does that make sense? That's why D is the midpoint because by definition midpoint. Any question there? Question? Awesome.
Two lines form.
If two lines form congruent adjacent angles, then guess what? Those two lines must be perpendicular.
It's like this and then it goes like that.
Then you don't have two lines forming congruent adjacent angles. They're not.
They're congruent adjacent. Two lines form.
If two lines form congruent adjacent angles, all the angle has to be 90. It can't be anything else, because then the two angles would not be congruent adjacent. It has to be congruent adjacent for every adjacent angles, right? All the adjacent angles must be congruent, right?
Okay.
Yes.
Why isn't there a theorem for like perpendicular lines that they're going to be?
Perpendicular lines, what? Well, what's the definition of perpendicular lines?
Before 9.
Yeah, there you go. So it's not a theorem, it's definition.
Is there converse in the theorem?
Okay, hold on. So, yeah, can I get to this next theorem now? Anybody want to guess then what the converse of this isosceles triangle theorem might be? That's what we're going to now. Converse of this theorem. Josh. Well, no.
Two angles of the triangle is congruent.
Good.
And the two
And the two
sides are
sides are what?
two sides are
Good, close enough. Okay, so that's you got the right idea. So here, write this down, guys. This is a converse. Again, this one doesn't have any name, so you have to know what it says. But it makes sense, right? Look, this is a converse of what we just did here in that theorem, isosceles triangle theorem. If two angles of a triangle are congruent, for example, look at angle B and C, right? If that's given to you, guess what? Then the side opposite of those angles are congruent, which are the AB and AC. Yeah. So go ahead and write it down. Does that make sense? Do you see why this is a converse of isosceles triangle theorem? Yes? Okay. Go ahead and write it down.
Is there?
Okay, then how would you go about proving this? Amy, what do you think? What do I need to show in order to prove that AB is congruent to AC? What is your key step? going to be, you think, for this proof, if we have to prove this? If I want to show that AB is congruent to AC.
Maybe the triangles are congruent.
Exactly. If I could prove that triangle ABD is congruent to triangle ACD, then you're done. Because those are the corresponding parts of the congruent triangles. How are we going to show that the two triangles... By the way, do you think we're going to use the same auxiliary lines as we drew before? Where it's the angle bisector of the angle BAC? Yeah, that's why we have this dotted line and you see the marking. So how are we going to show then the two triangles are congruent? Yechan?
If we use that, the first given,
Yes?
and then angle A, right? No. Oh, angle BAD and CAD are congruent.
Okay, that's fine. Because we drew that auxiliary line the way that it bisects that angle A.
What's the reason we drew the auxiliary line?
No. Because after you drew the auxiliary line, you say definition of angle bisector. That angle BAD is congruent to angle CAD, right? Because isn't that how we drew that auxiliary line? So that's the angle bisector of it. Okay, that's fine. Then what?
And then you say the second AD are congruent because they're common.
Okay, that's how you get it wrong. You cannot use, so you have the three parts, right? How come I cannot use those three parts? Angle B right here, and this angle, and then this side, and then angle this, angle C, and then, yeah. What are we using? Is that angle side angle?
Angle side.
That's angle side. Turns out there is an angle side theorem. We'll learn that later, but we don't know this yet. Okay, we don't know this yet, so you cannot use that. Okay. So how are we gonna do this, Kevin?
Since angle B and C are congruent,
Yes.
and the corollary 3, you can say that.
Oh, could we use this corollary 3? How many people say yes? We could use corollary 3. Raise your hand. Raise your hand. Okay. Let me show you the corollary 3 again. It says the bisector of the vertex angle of an what kind of triangle? Do we have an isosceles triangle? No. Guess what? You cannot use corollary 3 because corollary 3 states that you have to have an isosceles triangle. Do we have an isosceles triangle here? No. So almost, that's a good try, but you can't use that. So that's what a lot of people would think that no, because if you want to use it, then you have to have an isosceles triangle. We just know that the base angles are congruent. So then what do we need? So we cannot use, we need one more thing. 1, 2, okay, how about Jason?
BDA and CDA.
Exactly. We need to show that BDA is congruent to CDA. How are we going to show that those two angles are congruent? This is the key. Anybody? 2 people see it? Because if I could show that BDA is congruent to CDA, then guess what? AD will be the included side, wouldn't it? Okay. So how are we going to show that BDA is congruent to CDA? 2 people, 3 people, 4 people see it? People looking through their notes, that's fine. Yeah, remember that we had a nice, I think it was a corollary.
Oh.
Nicole, what do you think?
Yeah, I don't know, like, then isn't it like 2 angles, or, oh wait.
Yeah, you got that right. If 2 angles of,
Two congruent triangles, or wait, like 2 angles are congruent to like 2 angles of another triangle, and the third angle is congruent.
exactly right. If 2 angles are what? Congruent to 2 angles of another triangle, guess what? The third angles are congruent.
Oh!
You guys remember that one?
The angle B and C are congruent.
Yeah, because if 2 angles of one triangle is congruent to 2 angles of the other, guess what? Third angle must be congruent. Then we could use what? Angle side angle to show that 2 triangles are congruent. Then you could say AB congruent to AC. Very good. Any question?
Do I get the
Wow. I
Yeah,
don't even
you
know
get
these.
Nicole gets you get the you get the what is it? You get the medal. Go ahead. What? So here's our last corollary here. It says this. Yeah, from this theorem. Well, it doesn't have any number. It doesn't matter, right? Because there's only one from this theorem. An equiangular triangle is also equilateral. Converse. What do you call it?
It's a converse of that.
Oh, the other, yeah, you're right. An equiangular triangle is also equilateral. Now, how would you go about proving this here? Michael? Why should this be true? And again, this comes from the theorem, right? The previous theorem. That's why they're closely related. That's why they call it as a corollary, not a theorem, right? So why is this a corollary of the previous theorem? An equiangular triangle is also equilateral. By the way, go ahead.
I know, I think I know.
It's because of the previous theorem.
Yeah,
Okay, so what do they mean by equiangular triangle? What kind of triangle is this, guys? All the angles are congruent. So whereas this theorem above says only two angles, right?
yeah.
So guess what? Just like before, who could tell me? John?
It's like an equiangular triangle is also isosceles because the opposites.
No, you can't say equiangular triangles are isosceles. In our head, we know it is, but by using the definition, it says two. It has to be at least two sides congruent. What I'm trying to ask is, how would you go about proving this corollary if you had to?
I think I
Tony?
well, if you use the theorem twice,
Yeah, you use the theorem twice again, right? Yeah, if you use the theorem twice, you say, oh, B and C are congruent, but because it's equiangular, guess what? A is also congruent. So you say B and C are congruent. Hold on. So B and C are congruent, right? So what? AB is congruent to AC, but you use it twice. A and C are congruent, then the other sides are congruent. So,
Do this for homework.
right? Then what? All the sides are what class? Does that make sense?
Yeah.
Any questions? Okay. Good.
Don't get